All right, and we are live. Hello, everyone.
Hello.
Welcome, welcome. Hello. All right, awesome. So, welcome to our Fiveable cram for AP Physics. This will be our preview one, and I see some of you are in the chat. Be sure to send some messages into the chat to show that you are super excited for this cram. And just to introduce ourselves, who are we on this screen? I'm Shelly, and I am currently a junior at the Davidson Academy. I've taken AP Physics C, both the mechanics and E&M section. So I'll be here helping you all with AP Physics 1. I also have Joseph co-teaching with me.
Hi, I'm Joseph. I am also a junior from Pennsylvania. I'm so excited to teach AP Physics to you guys.
All right, awesome. So I'm seeing you guys trickling in through the chat. So be sure to send a message just so that you know how this chat system works. And we'll get started with intros beyond this. So as people are trickling in, we won't hop into the official material until in about like 5 minutes. So let's jump into our community agreements. So we just want to make sure that everyone in the chat, I think you guys are already doing this already, but we want to be supportive of each other. We'll be with each other for the next few nights of these cram sessions. So let's lift each other up, especially during this stressful process. Maybe AP Physics isn't the only AP that you're taking. There might be some other things that are also happening. So we want to make sure that we support each other through that. And of course, we want to be patient with each other. We're all learning together, cramming through that final material. So we want to be sure that we're patient and aware of each other. And of course, we want to be kind to each other. We're all real people behind the screens. Even though we can only really see each other through the chat, we are still people behind the chat. So be sure to be kind. That. Okay, awesome. So let's take a look here. So as we've mentioned, this is our first preview night, but if you like what you see, we do also offer a cram mode, and through our cram mode, it unlocks access to 40 prep books to ace whatever test that you've got on deck, and there should be a call to action at the bottom of the screen. If you click on that, then you can get access, or you can take a look at whether cram mode is right for you. Not only do you get these 40 prep books, and that's for like APs, ACTs, ACTs. I don't know if I mentioned SAT, but SAT and ACT, they sound similar. Anyhow, you get 24/7 access to over 200K unique practice questions. So definitely more than enough to practice. And also, you get tickets to all cram events and finales. So if you think of us as like Taylor Swift or something. It's like getting your access to one of our AP concerts. And you'll get 5 nights of review before the day of your exam, which is pretty neat. So definitely check that out. And of course, how do you make the most of a preview? So the way you can make the most of a preview is you can take notes during this. And this makes sure that you're active rather than just looking at the slides. This actually makes you think about the slides. But of course, you don't have to try to write everything down because there's going to be a lot of material. So just jot down things that you think you'll want to review. Just do whatever works best for you. And there's also a My Stuff, which has all the slides and the replays for you. So you could check that out as well. And then we also have the group chat, which we see some of you are using. And this is for sharing tips, tricks, and also to participate in the chat when we ask questions. And last but not least, we also have a Q&A tab. And this is for asking any question to us. And you can check in the comments for whether there's an answer to that question. Okay, so let's take a look at our cram schedule. Joseph, you want to take this one?
Yeah, just for our schedule, obviously today is May 3rd on our first free preview, but we have another preview out on May 6th just to see if you want to actually get into these previews. On May 12th is when the cram sessions actually start, and these will continue all the way until May 16th with our cram finale. And as I mentioned, I'm Joseph, and we have our host, Shelly, as well, and a bunch of people in chat, and obviously our designers as well.
Yep, of course, we're obviously all cats. wearing orange hats. I'm not sure what those are, but cats, yes. Okay,
Of course.
so
And just to
okay,
go over our agenda for today, we just did our welcome. We're going to talk about the concepts behind gravity and the forces associated with them. We're going to do a few practice MCQ questions along with one practice FRQ, and we'll finish it off with a Q&A. And obviously, follow us on Instagram, TikTok, YouTube, LinkedIn at Think Fiveable.
yep, awesome. And just before we get started, we want to launch a poll about how we are feeling about this AP exam of AP Physics 1. So are we feeling from a scale of 1 to 5? Are we feeling 1, meh, 2, okay, 3, not bad, 4, pretty good, or 5, I basically taught Newton? I'd be very impressed if you basically taught Newton because you're going to get that 5 for sure. All right. And we'll just wait for, half a minute when you guys in the chat are answering that. Awesome, awesome. And of course, if you have any tech issues, you don't know where to find the polls or where to find, like the quizzes or the slides that we'll be showing you, you can always let us know in the chat. And we also have some of our hosts in the wing, and they'll be able to help you out through the chat. All right, so let's see, I'm seeing a mixture of responses. We do have one person who said, I basically taught Newton, which pretty awesome. You're going to get that 5. Let's see, we're getting some meh, some okay, some not bad, some pretty good. Okay, so we have, a pretty mixed feelings about the exam. That's totally fine. We hope that with this preview and the other crams, we can hopefully boost that confidence so that we're feeling really good about the exam when we're going into it. All right, so let's take a look at universal gravitation. This is an overview of gravity in AP Physics 1. All right, so with gravitational fields. So any object can create a gravitational field, and this is done by pulling nearby objects towards it. So any object, this can be the Earth, where you might have noticed that when you jump in the air, you go back down, and that's the act of gravity onto you. And this is performed by the Earth, but any small item, perhaps the pencil that you are holding in your hand, perhaps the notebook that's right in front of you, that can also create a gravitational field. Now, of course, you are not being pulled towards the pencil, at least not very noticeably, and that's because the pencil has a really small mass, so its gravitational force is not going to be very strongly exerted onto you, and we can see that through a formula that we'll be showing you later on. And also the constant g, it's a lowercase g, describes the strength of a gravitational field. So on Earth, it would be 9.8 meters per second squared. On the AP, it might be 10 meters per second squared, but something around those two values. And on other planets, for example, the constant g would not be exactly the same. And then for gravitational forces, if an object of mass m enters a gravitational field g, it will experience a force called a gravitational force, and that's equal to m times g. So the mass times whatever gravitational field. So and keep in mind that mass is different from weight. So object's weight is equal to the gravitational force acting onto it. So weight would be referring to F of g that you see in this equation in the middle box, whereas the mass is represented by m. So mass would be in kilograms, and then the weight should be in newtons. And then acting at a distance, the force of gravity acts at a distance. And what that means is that the two objects do not need to be in direct contact with each other to exert a gravitational force on each other. So going back to that jumping example, when you're in the air, you are not in direct contact with the Earth, but you still feel a gravitational force because, well, it's only the distance between the two objects that matters. So they don't necessarily have to be touching on each other. So even if you're in the air, not touching the Earth, you still feel that gravitational force. All right, and moving on to Newton's law of gravitation. This is the formula that I was referring to earlier. So gravity is a fundamental force between any two objects, but it's very weak on a human scale. And specifically, the force of gravity can also be found using F of g is equal to big G times the mass of the first object and then the mass of the second object that we're observing. And then that is over r squared. And oh yes, and if you want to take a look at the slides that we're showing you, there's also a call to action. You can get a copy of the slides. So you can also follow along there. Okay, and specifically, any two objects each exert a gravitational force on each other. So going back to our examples, whether that be you with the earth or you with your pencil or you with your notebook, any two objects will be exerting a gravitational force on each other. Now, of course, it's the magnitude of those forces that we are interested in. So the magnitude of the gravitational force, that is directly proportional to both objects' mass. So you'll see in our formula somewhere in the top right, we have m1 and m2. They're both raised to the first power, and they're both in the numerator. And so that would mean that it's directly proportional to the magnitude of the gravitational force. And then we also have that gravity is one of many forces that follows an inverse square law. And if the distance between two objects is doubled, then the magnitude of the gravitational force is multiplied by 1/4. So, for example, like if r was equal to 1 and everything else was the same, if we replace r with 2, then we would have everything that we had before, but over 4 instead. And so let's see. We have a graph that shows this. I'll pass it on to Joseph. But oh yeah, before we pass it on, we have that big G is equal to 6.67 times 10 to the negative 11. So that value is really, really small. And that shows why the gravitational force between two standard objects like the pencil or the notebook is going to be really small. It's because of that gravitational constant. Okay, so now I'll pass it on to Joseph.
Just to show you how the inverse square law works, if we have a graph of the gravitational force against the actual r value, we can see that as the r value gets multiplied by 1, 2, and 3, the gravitational force actually goes down to being divided by 4 and being divided by 9. So just because the r value is squared, the effect of a multiplier gets squared. So we can see that the shape of the graph follows a sort of parabolic structure, or hyperbolic structure, as in it curves downward. So as the mass gets multiplied more and more, the gravitational force also goes down at a faster rate. On to the next slide from there. Just to show you about the independence of the mass, the gravitational force on an object is directly proportional to an object's mass. As we can see from the formula, if we multiply the mass by 2, the magnitude of the gravitational force also gets multiplied by 2. And we know the acceleration is equal to force over mass by Newton's second law, F equals ma. So the masses are able to cancel, and the acceleration due to gravity is independent of the mass. So we have that g is equal to the force of gravity over m, and that the acceleration is equal to the overall net force over m. So we know that the masses can cancel and acceleration is independent.
All right, and with those formulas in mind, let's practice with an example problem. So we have two planets here. So exoplanet A has a mass of 3.5 times 10 to the 24th kilograms, and exoplanet B has a mass of 9.5 times 10 to the 25th kilograms. And so we have that these planets are 7.2 times 10 to the 11th meters apart. So that's a lot of numbers. So we want to absorb all the information that we got so far. Let's take a look. Actually, maybe what we could do is let's practice. You guys try this problem on your own. I'll give you actually, what's the question? We want to know what the question is. So we want to do the following. So we want to first calculate the magnitude of the gravitational force of exoplanets A and B exert on each other. We also want to identify the direction of this gravitational force, and we also are assuming that no other significant forces are acting on either planet. Then we also want to calculate each exoplanet's acceleration. So if you guys in the chat could try that, I'll give you guys maybe like 2 minutes. So to whatever hour it is in your time zone, and then 15. So calculate the magnitude of the gravitational force, the direction, and also challenge yourself, see if you can find the acceleration of each planet. All right, it has been about 2 minutes. No worries if you didn't get through all of those parts. We know that was a lot in a short time, but hopefully you guys kind of got a start to this problem or have an idea of where this problem is going. So let's tackle the first part of this problem, which was to calculate the magnitude of the gravitational force that exoplanets A and B exert on each other. So for the magnitude, we're going to want to use our good old formula, good old friend. F of g is equal to big G times m1 times m2, and that's all over r squared. And, well, what values do we know here? So we know big G, that is given to you on the formula sheet during the exam, and big G is going to be 6.67 times 10 to the negative 11 meters cubed over kilograms times seconds squared. And then that's multiplied by the mass of the first object. And so one of our objects is exoplanet A. So we want to take the mass of that planet. That's going to be 3.5 times 10 to the 24th kilograms. And now we have the mass of our second object, which is m of 2. That's going to be exoplanet B. And that planet has a mass of 9.5 times 10 to the 25 kilograms. So we want to plug that into m2, and that's all over r squared. Now, r is the distance between the two objects. In this case, it tells us that the planets are 7.2 times 10 to the 11th meters apart. So we want to plug that into r. And if you plug and chug that into your calculator, you get 4.3 times 10 to the 16th newtons. So this means that both A and B, so both planets A and B, exert a force of 4.3 times 10 to the 16th newtons on each other. And I want you guys to predict in the chat, if you haven't already, which direction will these forces be pointing towards? So, for example, for the gravitational force that B exerts on A, well, does that force pull A towards B or away from B? So feel free to put, towards or away in the chat. Okay, I'm seeing somebody says force will be towards B. Do we have any other guesses? Okay, we have another towards. Okay, yeah. So I'm seeing a general consensus of towards each other, towards each center of mass. And yeah, that's right. The direction is that, for example, A would be pulled towards B, and then B would be pulled towards A. And that's because gravity is always attractive. The direction is going to be towards the other planet. And if that's a little hard to wrap around your brain, you can think about you and the Earth as an example. So when you're jumping in the air, you get pulled back to the Earth. So that's again you pulling towards the Earth and the Earth being pulled towards you. So that's another example of gravity being attractive. All right. And we have over here, let's see, stop and predict. Answer in the chat. So without doing any calculations, and no cheating on this one, not that we can see you, but don't actually calculate it. Will the acceleration of exoplanet A be greater than, less than, or equal to the acceleration of exoplanet B? And why? If you are able to, if you're able to back that answer up, that would also be great. Right. And we'll give maybe like 30 seconds. You could put A or B into the chat and an explanation. Okay, so in the chat, I'm seeing that A is oh yeah, actually I'm getting mixed responses. That's good. We've got some controversy. And so we're seeing that some of you are saying that the acceleration of exoplanet A will be bigger. Some of you are saying that exoplanet B is smaller. Ooh, okay, I love this. So actually, I'll toss it to Joseph for this one. So do you think exoplanet A will experience a greater than, less than, or equal to acceleration of planet B?
I think the acceleration of A would be greater than the acceleration of B because of Newton's second law. So Newton's second law states that the force is equal to the mass times the acceleration. The planets experience the same force pulling towards each other. And because of that, it just depends on the mass at this point. So because the forces are the same, when you divide the same force by a lesser mass, that would experience a greater acceleration. So because exoplanet A has a lesser mass, exoplanet A will also experience a greater acceleration as a result. And now let us practice with an FRQ. So just to read this out, an explorer plans a mission to place a satellite into a circular orbit around the planet Jupiter, which has mass of 1.90 times 10 to the 27 kilograms and a radius of 7.14 times 10 to the 7 meters. If the radius of the planned orbit is r, we will use Newton's laws to show each of the following. 1, that the orbital speed of the planned satellite is given by v is equal to the square root of gravitational constant times the mass of Jupiter over r. And part 2, that the period of the orbit is given by t is equal to the square root of 4 pi squared r cubed over gravitational constant times the mass of Jupiter. We're going to give you around maybe 5 to 10 minutes for this question. And maybe in the meantime, you can talk about in the chat what specific concepts you're going to use for an FRQ, how you would approach this, and just your general thoughts on the question. We're just going to give you around 5 to 10 minutes, and we'll check back in at around 7:28 maybe. Okay, guys. I hope you made some good progress on the questions. I see a lot of good things in chat. So just to go through a few of the concepts that you should probably notice about this question before actually starting it. So if we notice a satellite moving in a circular orbit, this is unnatural. What nature wants to do is always move in the same line, right? Newton's first law, object in motion stays in motion. But in this case, it's a circular orbit. So maybe we could use something with circular equations like centripetal acceleration or something with circular velocity or something like that. And other things we should notice is maybe we could use Newton's second law for this to make some associations with the centripetal acceleration formula. So moving on to the solution for the first part. And we have the question up on the slide just so you can reference that as well. So first thing you should notice, Newton's second law. So in this case, through using Newton's second law, we can see that F is equal to mac. Remember, the satellite is constantly being pulled towards the center of the planet. It's not simply that the satellite just goes off in one line. It's constantly being pulled towards it. And that's why we have the centripetal acceleration there. So we have F is equal to m times the centripetal acceleration. But also, we know that F is equal to the gravitational constant times the mass of Jupiter times m, which is the mass of the satellite, over r squared, because of the formula that we found earlier, Newton's law of gravitation, that the force, the magnitude of the gravitational force is simply equal to the gravitational constant times m1 times m2 over r squared. So we know that both of these equations hold, that F is equal to m times the centripetal acceleration, and also that F is equal to the magnitude of the gravitational force found on Newton's law of gravitation. So what we can do is actually just set these equations equal to each other. So we know that m times the centripetal acceleration is equal to gravitational constant times the mass of Jupiter times m over r squared. And these m's are the same thing. These are both the mass of the satellite. So what we can actually do is simply cancel out those m's and rearrange the terms, but we still have AC. AC is the centripetal acceleration, and we can substitute the formula for that as v squared over r. That is also on your AP Physics 1 formula sheet. So if you didn't remember that, that's completely fine. It's right on the formula sheet. If we take that equation and rearrange the terms and simplify, we get that V is equal to the square root of the gravitational constant times the mass of Jupiter over R. So I hope that makes sense. But obviously, if there's any questions, feel free to put that in the chat below. We can go back to the first slide. And I'll give you guys just a little more time for question number 2. And something that you could notice is that you can also use your answer for part 1 for part 2. And that's your little hint for now. Maybe we can take like 3 to 5 minutes just for this part. We'll join back at around 7:37. Okay, I I hope that was enough time for part number 2. Um, so just as a refresher, the period of the orbit is given by t is equal to the square root of 4 pi squared r cubed over g times the mass of Jupiter. So I don't know if you noticed, but I noticed this in chat that this is actually just the same as Kepler's third law. And if you notice that this is Kepler's third law, that's great. But you can't just say that it's Kepler's third law and move on. You just simply need to, you just actually need to prove it's true based on the equations that we found before. So if we move on to the slide with answer 2. Okay, so the first thing to actually realize here is, what is a period? A period is simply the time it takes for the path to repeat itself. And in this case, the path is just the path of the satellite, which is a circle with a radius r. In this case, the length of that path is just the circumference of that circle with radius r, otherwise 2 pi r. So to find the period, we can just use something similar to distance is equal to rate times time. The distance in this case would be 2 pi r. The rate would be the velocity of the actual satellite, and the time is the period. So if we rearrange some terms, we get that v is equal to 2 pi r over t, or also t is equal to 2 pi r over v. And we know that v is equal to, if you move to the previous slide, that that v is equal to the square root of g times the mass of Jupiter over r. We can take that equation that we found from the previous part, and if we move to the next slide and substitute that in, we get that t is equal to 2 pi r over the square root of g times the mass of Jupiter over r. And we can rewrite 2 pi r as the square root of 4 pi squared r squared, and just flip the fractions to get that t is equal to the square root of 4 pi squared r cubed over the gravitational constant g times the mass of Jupiter. And you need to show all of these steps in order to get the points for this question. You can't just skip the steps or say that it's Kepler's third law to get the points. And we'll move on to our next part of the FRQ. Or we need to do a poll to have some feedback on this.
Yeah, I believe we do have a poll just to ask or kind of gauge how we felt about this, or at least these two parts. So I believe that's visible now. So did you get the questions right? Yes or no? And it's okay if you did not get them right, because that was definitely a lot in a short time. But just to see how we're feeling, do we know how to get the question now? Or did you guys already know how to do this? So we'll give you like a minute to answer that poll. And if you have no idea what's going on, that is also okay. You can let us know in the chat, and those of us in the wing would be more than happy to help you. All right, so wow, this is beautiful. There is a 50-50 split between yes and no. Okay, yeah, awesome. So if you guys are still not really sure about how to approach this problem, throw a message in the chat and we'll help you. Okay, so we've done part A, and you'll think we moved to part B, right? But actually we are moving to part C, because part C is an interesting question. So for part C, suppose that the injection of the satellite into orbit is less than perfect, and for an injection velocity that differs from the desired value in each of the following ways, sketch the result orbit onto the figure. So in the figure that is shown at the bottom of the slide, J represents the center of Jupiter, and then the dashed circle is the desired orbit, and then P is the injection point. And so this question wants you to describe the resulting orbit qualitatively, but also just specifically too. And so for this part, we want to see what happens when the satellite is at the desired altitude over the equator, and its velocity vector has the correct direction, but the speed is slightly faster than the correct speed for a circular orbit of that radius. All right, I'll give you guys around 5-ish minutes for this question. We'll meet back at whatever time zone you're in, and then 48 minutes after. So you can pop whatever you think into the chat, and we'll get right back to you in 5 minutes. All right. So I'm seeing a lot of good thoughts in the chat. I'm just hopping in a little early just because there's already lots of good stuff. So taking a look at what you guys said, it seems like a lot of you are saying that this satellite is going to enter an elliptical orbit as opposed to the circular orbit that is shown on the screen. And yes, we would get an elliptical orbit. And so let's see why that is. So we have that the speed here is slightly faster than the correct speed. So if we had the correct speed, then P would go into that dotted line as we established that perfect circular orbit. But if it's slightly faster, now P has to go, or now the satellite has to go slightly further away from from Jupiter, right? Because otherwise it's going to kind of fly off into space. So if, like, for example, like if J wasn't there, P would just keep going straight and just into nowhere. And so the reason why also P doesn't just go into like a larger circular orbit is because the force that's felt between the satellite and Jupiter does not change. The gravitational force between them is still the same. And that's because with our formula of f of g is equal to big G times m1 times m2 over r squared, none of those values have changed. Like the masses haven't changed. We're still kind of the same distance away-ish. And so although throughout the elliptical orbit, we will be at different radii, but the gravitational force that the satellite and Jupiter feel towards each other, it's still going to be enough to keep the satellite in an orbit around Jupiter. It's just that now it's in an elliptical orbit as opposed to a circular one. Okay, so let's take a look now at our practice quiz. So our practice quiz is here. So if you guys could scan the QR code just to jump to it. Let's see. And there's also, you might want to use the call to action button that just popped up as opposed to the QR code, just to make sure that everyone is on the same quiz. So to get access to that, I'm seeing some of you have already joined the quiz, but you'll see that at the bottom of the Crowdcast, you'll see a practice quiz. If you click on that, you'll get to the right quiz. All right. And I'll share the screen with the quiz just to make sure everybody gets to the right one. So if everyone who maybe scanned the QR quiz from before could scan this one that's on the screen instead, this should get you to the correct quiz. So I'm seeing 10 of you already joined. I want to see that number go up. Oh, 8, now it's 10. Okay, so we want to make sure everyone gets to this quiz. I'll give you guys like another minute. All right, when we hit around the 17 mark, we're going to begin. So 2 more people. Okay, and that just happened. So we are going to start the quiz. All right, so let's take a look. So, okay. Oh, good point in the chat. Yeah, is this the right quiz? Okay, let's see. This may not have been the correct quiz. Let us retrieve the correct quiz. Let me go back to the practice quiz slide. Let's see. Okay. Give us some time to get the correct quiz, because that one was for a different night. So that one was not about gravitational. All right. We have a new button for the correct quiz. Let's see. Hopefully this is the right one now. So let's take a look. Okay. Awesome. So this should be the correct quiz. Now it says Preview 1 quiz. That's the right one. So if you guys could scan the QR code and join this one, this should be the right one. Okay, so once again, when we hit that 17 mark, we'll begin. And we're just going to do this quiz. We do have 3 minutes for this quiz now. But when we get to whenever it's 55, then we'll stop the quiz. So, all right, let's begin. So, for our first question, we have if planet X orbits star Y at thrice radius compared to planet Z orbiting the same star, so with the same star experience, what change relative force experience Z assuming similar planetary composition, sizes, and masses? Right, and I'll give you like around a minute for this one. Okay, it has been around a minute, so let's reveal the answer. And I see that 13 out of 22 participants answered. If you guys want to get in like your last minute answer, you can even guess. That's okay. You've got 4 options. You've got a 25% chance. Okay, let's reveal our answer. All right, and the correct answer was that the force that X experiences is 9-fold weaker, and that's due to the inverse square relationship of radii orbits. And yeah, that would be right because we're given that planet X orbits star Y at thrice the radius. So that means planet X is 3 times further compared to from star Y compared to planet Z. So with that r squared in the denominator, when we had that f of g, this inverse square law would mean that the force that X experiences has to be 9-fold weaker. And where that 9 comes from is that 3 squared. All right, so let's take a look at our next question. Okay, so if a uniform density planet suddenly became denser in the core while maintaining the overall mass and volume, what effect would the gravitational acceleration at the surface experience? So we'll give you guys another minute for this one. All right, that was about a minute, so let's take a look. And okay, it looks like it's D. Okay, so let's see why that is. So D says that the gravitational acceleration at the surface increases, resulting in a stronger localized mass concentration, leading up to an intensification of the gravitational pull towards the condensed region. Okay, let's see why that is. So it's saying that the density planet suddenly became denser in the core while maintaining the overall mass and volume. Ooh, this is interesting. So it looks like that the mass stays the same. So we're not going to be depending on M1 or M2 because neither of those change. So let's see. So there's a stronger localized mass concentration. let's see. Yeah, exactly as said in the chat, neither mass nor radius between the two things change. So yeah, exactly. M1 and M2 don't change. Of course, big G doesn't change. And let's see, that's interesting because, wait, it looks like there's a lot of controversy on this one. Okay, so some of you are not able to understand the question and answer. Okay, so for the question, it's if we had a planet and it suddenly became denser in the core while maintaining the overall mass and volume. So what that means is that the planet, its size is not going to change, but what does change is the distribution of mass throughout. So the mass overall of the object doesn't change, but it just means that the mass is more concentrated at the core of this object. So that means if you're like at the center, then you're going to be looking at some really dense material. But if you're at the edge, the material around it is really dense. You can think of it as like Jupiter, where its center is more dense than at the surface. Like the surface is made of gas, which is not very dense, whereas the center is a little more dense. So that's the setup of the question. And we're looking at the gravitational acceleration at the surface. Okay, so actually, we think that there might be a problem with this question. So some of you have pointed this out in the chat, but it might actually be C. So C is saying that the surface gravity reduces as the mass redistribution concentrates centrally, which implies weaker interactions with the outer shells of a spherical object. So when we had an object that was uniformly distributed, we didn't have this to consider. But if we had more mass at the center, that means if you think of like the planet as being composed of a bunch of atoms, that means more of the atoms are concentrated at the center. So that means there's more objects that are further away from you. And from what we know of f of g is equal to, with the inverse square law, if something is further away, then it's going to feel less pull, or the gravitational pull will be weaker between the two objects if it's further away as opposed to if it was closer. So actually for this one, it should be C, because if there's more mass at the center, that means more of the mass is further away from you. So this one is definitely really tricky. Even this deck thought it was tricky. That's okay. If that was kind of confusing, you can let us know into the chat. Yeah, so we think that it's actually C was the correct answer. So we can kind of like argue between what the correct answer is. So let's take a look at our next question. I think we could make this last question the last one. So let's take a look here. So what happens, it's a lot shorter of a question, what happens to the gravitational force between two masses when the distance between them is halved? Right, we'll give like a minute for this one. All right, that was about a minute for this one. Let's reveal, and I'll toss it to Joseph for this one. So Joseph, why does it increase by a factor of 4?
Yeah, so by the Newton's law of gravitational force, we know that the force of gravity is equal to the big G times m1 times m2 over r squared. But the important thing there is that the r is squared and in the denominator. So because the distance between them is being halved, the 1/2 r is in the denominator and the 1/2 is being squared. So when the 1/4 is in the denominator, that's being flipped around and it increases by a factor of 4 instead. So being divided by a 1/4 is just multiplying by 4. So that's why it increases by a factor of 4. And I
Alrighty,
think that'll be the
awesome.
last question for the night.
Yep, so let's hop back to our slides. So now will be our Q&A. So if you guys have any questions on the session, any questions on the problems, now is your last chance to ask all of those questions in the chat. And there will be definitely more cram quizzes in the next preview. There's going to be another preview coming up, and of course in the actual cram sessions. So if you were really bummed out about why there were no more questions, don't worry, you'll get to see them once again in the next few sessions. Alrighty. Awesome. So now we'll pop out a survey for you guys. Please complete that. Basically, how you thought about this preview session. What do you like to see? And yeah, awesome. See, and if there's anything else, let us know. All right, and yes, of course, we can go back to the socials. If you want to follow us on socials, we've got LinkedIn, we've got YouTube, we've got TikTok, we've got Instagram. It's at Fiveable for all of them. So yeah, that's all for tonight. If you guys don't have any more questions for us, then we are finished with all the material, and we hope to see you in the next sessions. Bye, everyone.
Thank you. Thank you all for coming.